So, hello all. In this video, we'll be seeing about oscillators. So, let's continue with it. So, what is an oscillator? An oscillator is a circuit that has all parts or complete set of a circuit, which will provide oscillations that are not damped. That is, they won't decrease with time without having any specific input from any other source. That is, without having an input from the function generator or any other equipment like that. So these oscillators will provide you an oscillation without any of those inputs given. So let's see about the parts of an oscillator circuit. So as we said before, that oscillator is a complete set of parts of a circuit. So these are the parts. That is, you'll have a tank circuit, transistor amplifier, and a feedback network. So a tank circuit is this over here that you're seeing, a combination of inductor and a capacitor. That's what you call as a tank circuit. And you have an amplifier, transistor, and a feedback network. So this is what is an oscillator consists of. That is a basic diagram for it. And now we'll see about Barkerson criterion for oscillations. So this Barkerson criteria is something that a specific oscillator or any oscillator circuit needs to get validated with, or they need to have all these criterias present in them so that they provide oscillations that are not damped or they provide undamped oscillations. So the first thing is that you need to have a gain, that is beta A should be equal to 1. And then you need to have a phase shift through the loop that is either 0 or an integer multiple of 2 pi n. As you can see over here, those are the 2 points given over here. It asserts that if A is given, is the gain of the amplifying element in the circuit, and beta is the feedback path transfer function. So beta A is the loop gain and around the circuit's feedback loop. The circuit will maintain steady state oscillations only at frequencies for which the loop gain is equal to 1. As I said before, it should be equal to 1. And then the phase shift through the loop is either 0 or an integer multiple of 2 and pi. So now we'll see about LC oscillators. In oscillators, there are two types of oscillators, RC oscillator and LC oscillator. But over here, we'll only discuss about LC oscillator in this video. So LC oscillators are used for generating high frequency signals. LC oscillators preferred because at higher frequencies, better results are obtained with LC tuned oscillators. So the transistors, BJTs and FETs or amplifier op-amp can be used in LC oscillators in the frequency range of 100 kilohertz to 100 gigahertz. The quality factor of LC oscillator circuits is much higher than that of RC oscillators. So that's the reason why we're actually speaking about LC oscillators in this video, and we'll go further with it. So there are five types of LC oscillators. There exist numerous types of LC oscillators used according to the desired application. Based on the output frequency of the oscillations to be used, LC oscillators can be classified as Colpitt's oscillator, Hartley oscillator, clap oscillators, tuned collector oscillators, tuned base oscillators. Over here, we'll only see about Colpitt's oscillator for now. So Colpitt's oscillator is one of the important LC oscillator. So this is the diagram of, or the circuit diagram of the Colpitt's oscillator, where you have a tank circuit, a transistor amplifier, and a feedback given to it. So over here you can see that the tank circuit is connected in parallel to the base and the collector region. So we'll read about it. Colpitt's oscillator is one of the important LC oscillator. In the Colpitt's oscillator, a parallel LC circuit is connected between collector and base, or between drain and gate. So if you're using a BJT, it's going to be parallel to collector and gate, and for collector and base, and for FET, it's going to be drain and gate, with a small tuned circuit voltage applied in the emitters or source as shown below. So now feedback is achieved through the capacitive divider circuit used in the Colpitts oscillator. In this LC oscillator type, the ratio C1 by C2 determines the feedback ratio. So here you can see that there are two capacitors, and this capacitor ratio is what decides the feedback given to it. And by changing the ratio of this C1 C2, you can also change the feedback ratio also. And here you can see that the circuit diagram is changed with or you can it's replaced with an equivalent AC model. So here you can see that there's an equation given to calculate the ratio of C1 by C2, and on solving it, we get it as C2 by C1 equals to GMR, and this is the ratio that you need to have to get a proper feedback ratio or a high feedback ratio. So as I said before, that Colpitts oscillator can be made either with a BJT or an FET or an op amp. So if you see a circuit of Colpitts oscillator with an op amp, this is how it looks. So it's mentioned over here. The Colpitts oscillator can also be designed using op amps, as op amp provides greater frequency stability. Although the operation and the value of output or resonance frequency will remain the same for both, the circuit of the op amp based Colpitts oscillator is shown below. So here you can see that we have an op amp in place of the transistors or or that is BJT or FET, where you have a VCC connection given, a ground, a tank circuit. Feedback is also given over here. That is given to the inverting terminal, and an output can be given, collected or read on the other side. So now applications of the Colpitts oscillator. The Colpitts oscillator has a frequency range of 20 kHz to 2 MHz. High frequency sinusoidal sine signals can be generated with the help of the Colpitts oscillators. This LC oscillator type is also used in radio and mobile communication systems for high frequency signals. So over here, because we have a high frequency range of 20 kilohertz to 2 megahertz, these can be used in various fields like in radio and mobile communication systems for high frequency signal generation. So this is all about oscillators and Colpitts oscillator. Thank you.